So we continue today the OPF part. This is what we saw last week. Last week we saw the optimization techniques that are used for solving optimal power flow problems. And we saw that the optimal power flow problems for AC grids is in general something that is too hard to be solved exactly. So we have seen various linearization techniques, the DC OPF approximation, and sequential linear programming. We have also spoken of duality, a topic that is used for computing marginal prices, but also, as we will see today, will be used for studying robust forms of optimization. So the topic today is robust optimization, or in general, handling uncertainty. Last week we saw a problem where we assumed everything is known. We had a classical optimization problem where we have a plant, which is in our case the electrical grid, state variables that are the flows on the lines, for example, and control quantities that are the set points G2 and G3 of the generators. G1 is also a state variable because it is the slack bus here. When we studied this, we assumed everything to be known. In reality, in grid management tasks, we always have some uncertainty somewhere. In the traditional grids, the uncertainties are about the loads. So here, I'm assuming let's redo the same problem, but instead of saying the load at bus 1 is known to be 100 megawatt here, let's assume there is some uncertainty of plus or minus 10%. Right? This uncertainty comes from forecasting, for example. The loads, when we do these exercises, we are, of course, doing it a bit ahead of time. If we are doing a dispatch plan, perhaps we're doing that one day ahead. If we're doing voltage control, we might be doing that a few seconds ahead. But in any case, there is some uncertainty about the loads. The uncertainty depends on what the loads are and what the grid is. For a very, very large grid, for example, for the grid of France, the transmission network of France, the uncertainty about the loads is very small because we have a huge system and there is laws of large number that make that the individual variations are more or less cancelled out, and the uncertainty of loads comes from human behavior. So if you're able to forecast that there is a hockey match on Saturday evening, that there is nice weather on Sunday, you can know more or less what people will do. So large companies that run large grids do this using sophisticated machine learning and forecasting techniques, and they forecast the loads with an accuracy for very large countries at the aggregate level of order of 1%. Of course, if you do that at a smaller scale, if you're doing voltage control on the EPFL campus, for example, which we're not doing because the EPFL grid, like everything at EPFL, is over-dimensioned, so there are no voltage problems. But in other parts of Switzerland, there may be voltage problems if the grid has been built over time by adding new settlements, new buildings, and then trying to extend the grid rather than building a new transformer or pulling new cables. Then you might have voltage problems, and in that case you need to do a forecast at a much smaller time scale, smaller space scale. In that case, you will have uncertainties that may be up to 10–20%. I said load, that usually means the consumptions, this beamer, the lights, the heating systems. But today the loads are not only consumptions. Why? Distributed generations, exactly. In the case of EPFL, there are solar panels on the roof. They are not, from the grid viewpoint, they are not fed to a separate grid that would be called the grid of generators. That's not the way it is. They are just fed to the same transformers. So we speak here of the net load. So the net load is the true load minus the production. And in some cases, the net load might be negative, which means a load might be, in fact, generation. When we add the net loads, then we have much more variability. solar PVs in particular are easy to forecast, roughly speaking, if we know the weather forecast. However, they're affected by clouds. So if there are cloudy days, like today, for example, the production can go down by 30 to 60% when clouds passes, and it's very difficult to forecast clouds exactly on a given neighborhood. So to make a long story short, the load forecasts is usually from very accurate to 10-20% accuracy. There might be other reasons for randomness. For example, you might want to do something that assumes that you might have a failure of at least one device. We don't do that on this very small grid, but this is also done in larger grids, where if you have n generators, you might do a plan assuming 1 out of the n generators, or in general k out of the n generators, are in a random state, which is on or off. So you may want to have the system operational, assuming all this uncertainty. Here, what we will discuss more precisely is when we have continuous uncertainty. That means inequalities, like here. How does this affect the dispatch plan? Right. From a control theory viewpoint, we are in front of what is called a stochastic optimization problem, or an optimization problem with uncertainty, or a robust optimization problem. Those are all generic terms that may mean specifically different things. We'll talk about it when we see the specific instances of the problems. But the terminology is usually that is usually accepted is to say that the random thing is called a disturbance. In other fields of mathematics, we would call it a random variable. Here, it's not always modeled using stochastic frameworks and distributions, sometimes just with inequalities. So we invented a generic term that is called a disturbance. So from a control and optimization viewpoint, we're in front of an optimization problem where we have a state. We have a state equation, which is the equations of the grid. We have control. Those are the things we have to decide upon. And there is disturbance. So we can view it also as a game where we are in front of a big machine or a big system. We have to tune some knobs to find the values of some parameters. And then an adversary, nature, randomness of users, will play something called a disturbance. And we have to find control that will work well under all conditions of the disturbance, or practically all. So if we look in detail at this problem here, we have to choose the set points of the two generators, G2 and G3. As we said, the first one is the slack bus, so there will be instantaneous power balance in the entire system, so G1 will adapt. And let's assume the cost we will pay is the cost of the two generators, G2 and G3. The slack bus also has a cost, we assume. And we'll have to pay for this cost. Now, the new thing is that this cost is unknown in advance. So we have to buy something that we don't know exactly the cost, right? So it's like if you decide to go somewhere with your car, you will have to budget a certain amount of money for the gasoline. You will not know exactly how much you will pay, but you will have to pay for that. Right? Furthermore, the choice of the set points of the control must work for all values of the disturbance. What does that mean? Well, we have limits here, limitations on the power flows that can go on the grid. So I cannot use any fixed value here and hope that it will work in front of all uncertainties. It may be that if the L load here is very variable, we are forced to have a power flow that is very large on this line, and it might make the problem unfeasible. So when we have disturbances that have very large variability, very large range, we will be confronted with this problem. We will see that we must choose set points, control actions, values of the controls that work for all values of the disturbance, and sometimes it may not be possible. So some robust control problem might be infeasible. We'll see some cases of that. So we see here that there's a separation in the variable part of the load that affects two parts of the problem we had formulated. The first part is how do we formulate the cost that we want to minimize, given that the cost is now something that is unknown. And the second thing is that how do we formulate the constraints, the fact that the constraints must work in all cases. You will see when we do that in practice that the most difficult part is to adapt the constraints. Finding controls that work for all constraints, that is the part that is the most difficult in practice. A classical way to formulate such a problem is to cast it as what is called a stochastic optimization problem. Stochastic optimization problem assumes that the disturbance is drawn as a random variable. So we have to choose some control parameter. I call them generically U. So our U in the case before was G2, G3. Nature or our adversary or human beings will choose some disturbance that we assume to be known in a specified set. And the system state is given by the Planck equation that we assume we know. In the case of a grid, we know exactly with the admittance matrix formulation, we know this equation. So the state will be a function of what we have decided and of the disturbance. And one of the major constraints we have is that the state must be feasible regardless of the disturbance, and we will pay a cost that depends on our action and the state here. So that's a fairly generic formulation here. In the framework of stochastic optimization, what we do is for the cost, for the thing we minimize or we optimize, we take the expected cost. Expected cost means we assume that we can say something about the distribution of the disturbance. Not only its bounds, but also something about the distribution. If we can say something about it, we can compute the expected value of the cost of u and x when x results of f of u and d. So the random thing now is d. So if I would write this in all detail, the cost of u and x is a function of u, our control, and the disturbance d here. So u is a control parameter, d is a random variable. For any value of u, I can compute the expected value of this with respect to the random part d. I obtain what I can call C bar of u. And then the stochastic optimization problem can be formulated as follows. So the simplest formulation is this one. It consists in saying, I would like to minimize the expected cost subject to feasibility of the problem for any value of the disturbance. This is one formulation. It's not the only one. Here I said the constraints are satisfied with certainty, with 100% probability. Very often we will find that this is too demanding. If we want the constraints to be satisfied with 100% probability, it might be unfeasible. So very often, and we'll see what one example, what we try to do is to find a subset of D where with probability very large, 99% for example, the constraint will be satisfied. Which means we accept the fact that with some probability we fail. Right? In a grid, the probability of failure is non-zero and is accepted. So the grids we accept as a okay behavior if it fails 2 hours per year, which corresponds to probability that of failure that depends on the time scale on which you are operating. If you're doing this for the next day, that means you should have a probability of failure for the next day, which is such that when we accumulate those probabilities over an entire year, we get maximum 2 hours per year, which is 99.99% over the year. Right? So the probability of failing over a single day must be much, much smaller. Those are this is the most general form of stochastic optimization, where we have also some probability in the constraints here. So let's apply this framework to our example. I use here to simplify the DC approximation. We can of course do that with any convexification we have of our problem. but there are many technical problems. The more sophisticated the linearization is, the more complicated the equations will be, but the framework is always the same. So I take the simplest framework here. Those are the equations we have of the grid, so the state equation, when we replace the AC equations by the DC approximation. Then what we want to minimize is the cost of the set points G1, G2, G3, right? So here I have separated an equation for the cost of G1. So this is the power balance equation with the DC equation, with the DC approximation. And here I put a bar over L1, L2, L3 to express that the bar is the expected value of L1, L2, L3. Here I'm assuming that L1, L2, and 3 are between those bounds here. And I'm making some additional assumption. I'm assuming also that the expected value of L1 is the middle, which means it follows some distribution which is symmetric, for example. For example, uniform, but any distribution that has the property that the mean is at the center would also be okay. So I assume here L1 bar is 100, for example. Since the cost here is also linear, the expected value of the cost is the cost of the mean. So the cost of the mean cost will be the cost of G1 in expected value will be this, which is G1 bar. Then G2 and G3 are our control variables. So their expected value with respect to the disturbance is G2 and G3. So this is what the C bar function becomes. Then we have all those equalities for the true and random values. And those are the grid equations that we had before. When we translate them into the DC approximations, we find those inequalities of the angles that corresponds to the power flow limitations on the lines. And we also have the inequalities on the power injections at the different generators. So this is the same as before. And what is new, in addition to the cost, is that here we find the condition that those inequalities must be true, particularly those ones, for any value of the disturbance within the specified bounds. So this quantifier for all L1 is the new and annoying thing. That's the thing we need to get rid of, and we'll see techniques to do this. Okay, this I have explained already. So the next step to solve this optimization problem is to make it appear, one possible way is to make it in the framework I gave before, where we have only a control and disturbance. So I need to remove the state from the equations. Right? If you remember the formalism, this is this one. We have a state equation, which is x is a function of the control and the disturbance. And at the end, we want to say that the control and the disturbance is feasible for any value of the control, so for any value of the disturbance. So this is a constraint here, which is a constraint on U only, on the control. Right? There's the letter D, but since it is for all D, the result is a property of U. So here I have eliminated X. So that's what we will now do for this example. So the X is the theta here. Theta and G1, G2, G3 are the control. G1 is the state that results from the control and the load. Those are given by those equations here. So if I play G1 and G2, G3, if nature plays L1, L2, L3, we have from the DC approximation equalities, I can reconstruct G1, theta 2, and theta 3. Right? So since those are all linear, of course, we've linearized everything, they're all linear in the control and in the disturbance, then the inequalities I have here can be translated into linear inequalities into the disturbance and the control. And if we do this, this is what we find. We find the control G1, G2, G3, and the disturbance. And when we eliminate all the thetas and G1, we find those 4 lines of inequalities. That gives 8 inequalities here, plus those 4 inequalities on the controls G2, G3. So this is the problem that we have to, or those are the constraints of the problem. Right? So if we go back, of course, if we look at this, we can't, we are too close to the details. We need to abstract it a bit to solve it. So if I abstract it, I see that I have a problem of the kind, minimize some function of the control u, because I've taken the expected value. C bar happens to be linear, but here the focus is not so much on whether it's linear or not. Subject to constraints. Now the constraints are all linear inequalities. We have, for example, here, G2, G3, L1, L2, L3 less, so that is one inequality, and another one, so I have 2 inequalities here that are linear in the control G2, G3, and the disturbance here. So in general, I can write capital J linear inequalities that have the generic form for a linear inequality. It's linear in U and D, so I call A and B the coefficients that are in front of U and D. So the index J is for the jth line of inequalities, and the transpose is because this is a line of coefficients here. So each of those corresponds to all of those inequalities, and they have to be true for all values of the disturbances that are themselves defined by inequalities. So the disturbance is L, so those are the constraints on the disturbances, and we have here how many inequalities for the disturbances? 6, exactly. Simple inequalities here, they are independent inequalities. In general, we might find more complex inequalities have dependencies, so I write them in general in the form of a vector of that depends linearly on D less than C. So here C is a vector, and the inequality term means every coordinate of this vector is less than the coordinates of this one here. So this is our first prototype of a robust linear optimization problem. It's called robust because there is the for all D here. So the robust means the disturbance is assumed to take values specified by some bounds. So the problem now that we will solve is how to solve it generically, once for all the problems of this type here. So we have a problem where we minimize a function of the control, where the control and the disturbance are subject to linear inequalities that are fairly simple here. The linear inequalities separate the control and the disturbance. And the disturbance themselves are also subject to linear inequalities here. So the problem is how to get rid, we will see that it's possible to get rid of the disturbance, which is annoying because of the for all sign here. And the key step is to understand how to do it formally, in particular, how to get rid of the for all step here. Here I'm proposing 2 methods. I'd like to ask you to tell me which one you think is correct, if any. And the majority says C, which is correct. But the important thing is, in fact, not so much the important thing is to understand the method that leads to this conclusion, because that's the method that we use in general for all robust optimization problem of this specific form. The key argument is that we had something that says this is less than a number of this inequality is true for all value of the parameter D1 that itself satisfies a constraint. Then the key step here is to say that this is equivalent to saying that it's less than the minimum. So saying that an expression is less than a function of d1 for all value of d1 is the same as saying that the expression is less than the minimum. Strictly speaking, it's the infimum, but here we will not do the distinction between the two. So that's the key thing, right? You're smaller than a number of things for all value of the thing if you're smaller than the smaller. That's the key step that we will use for all kinds of robust optimization technique, right? Therefore, here we apply this to 10 minus 3d1, so we separate between u and d. u1 plus 2u2 is less than 10 minus 3d1. So we have to say that this is less than that for all value of d1, so it is the same as saying it's the minimum for all value of d1 that satisfy the constraint of 10 minus 3d1, which was the proposed answer here. So that's the key step that we will always use for such problems. Then the second step simply is true because now we have an optimization problem to solve, an auxiliary optimization problem. And this one is easy to solve because it's single dimensional. Anything single dimensional is usually simple. The minimum of this, that's a decreasing function of d1. So the minimum is obtained when d1 is larger, which is 5, and that gives minus 5 here. So the minimum of this is minus 5. Therefore, this is the same as minus 5. A and B, in fact, are the same. And A is equivalent to the original problem, so both are equivalent. Well, if you're able to solve it for this example, then that's exactly what we will do in the generic case for this type of problem. So I rewrite here the problem we had to solve with those inequalities. We have not one inequality like in the quiz, but a number of them. Then what I will do is, for each of those inequalities, I will separate the control and the disturbance. So I will say that I have to, it's the same as AJU less than gamma minus BD. And then I have to take the minimum of the right-hand side minus BD plus gamma for all value of D. This is now a linear program. It's an optimization problem where everything is linear. So that's a linear program that we can solve. There is one such program per constraint here. So I have to solve a large number of linear programs, but solving linear programs is a routine thing for MATLAB or for many solvers. Let me call Hj the optimal value of this problem. It's a problem that depends, that has only one optimization variable, that is D, and it does not depend on U. So I can call Hj the optimal value, which is a constant if the coefficients here are constants, which we assume. Therefore, this constraint, the jth constraint, is equivalent to a linear constraint on U with a right-hand side that we have computed by solving this auxiliary problem. In other words, what we can do is to replace each of those inequality that has the quantifier by an inequality that has no variable D. That is, in other words, we were able to explicitly remove the dependency on D. And that now becomes a standard optimization constraint. Like we did in the quiz in answer B, we had minus 5 that did not depend on D here. So this is the generic methods for taking care of robust constraints that are well separated between the U and the D. It's fairly simple intellectually, but of course we will need to solve one optimization problem per constraint. So there will be many intermediate optimization problems, but since they are linear, if they are linear, that's tractable. Return to our example and see what happens. We had all these inequalities that now have put in numerical form, and we have inequalities that depended on D, which was L in our previous example here. So I had this 1, 2, 3, 4, 5, 6 inequalities. So I solved 6 linear optimization problems that are not very difficult because the constraints on L1, L2, L3 are rectangular constraints. And that gives me those 6 constraints here where now there is no disturbance. L1, L2, L3 have disappeared. Of course, I've done that with MATLAB, Doing that manually is doable for a few people, but most people need a computer. So this is what we obtained. Those are the robust constraints we had at the beginning that were, not robust. So by doing that, we've seen that we needed to work on the constraints. It's done. And I obtain this thing. Now if I change the bounds, so this was with those bounds that are written in red, 100 plus or minus 10. If I change the bounds, I will change the optimization problem that I had in every inequality. I will change the set over which the L varies. I'm computing a max or a mean over all the possible values of the disturbance. If I change the bound, of course, the constraint will change. This is what I obtain if I add the uncertainty, assuming the first load here has an inaccuracy of 50% instead of 10%. And the last one, an inaccuracy of 20% here. Those are what the constraints become. Of course, the coefficients remain the same everywhere. It's the right-hand side that vary here. Sorry, there are, I said 6 a minute ago, there are 8 inequalities here. Now, if we observe those inequalities, what can we say about them? That's a problem that's easy to solve because, well, if you look at the first line, it's clearly infeasible, right? The left-hand side is larger than the right-hand side. So there is no solution to that problem. That's an optimization problem where the set X of the constraints is empty. There is no feasible point. Right. Which was not the case when we had that level of uncertainty, right? We had, well, depending on G1 max, but we had we had some correct values here. So the first observation to do, when we have a robust optimization problem, we will discover the exact bounds by solving the bounds here, by solving optimization problems to remove the D, and then we will see a posteriori, not a priori, we will see whether the problem is feasible. And it may be that the problem is infeasible. In that case, it's impossible. It's impossible, in fact, the problem is of the G1. It's impossible to find a set point of G1 that will satisfy all the constraints in this range here. There is too much uncertainty. It's unfeasible. So if you are running Swiss Grid or RTE in France and you find such a thing, then you need to know it in advance, and then you'll need to fix the problem somehow. Fixing the problem by changing the generator set point, curtailing the load or doing something, or refining your forecast, but you will need to do something. This problem is unfeasible. It's unfeasible, but unfeasibility is simply an illustration of the costs of uncertainty. Here, I'm showing the optimal expected cost. So the cost will come from setting the values here. And then the true cost, we don't know exactly. It will depend on the L1, L2, L3. But we can also observe something on the expected cost. So the value, even if the true value a posteriori are exactly the middle value. So the things we had forecasted, the point forecast, 100 for the loads, are exact. But we still don't know whether they will be exact. So we are forced to put an uncertainty bound around them. So the value I'm showing here on the y-axis is the value of the cost, assuming the forecast was exact, but assuming we had some uncertainty a priori about the forecast. That uncertainty forces us to be more conservative. By being more conservative, we need to take a set point of the generators that may not be the optimal one if we had less uncertainty. So that clearly shows up here as we increase the uncertainty on L3. So at 0, that I'm redoing the same problem as before, but I assume the uncertainty on L3 is 0. In fact, I've rescaled the uncertainty on all the, by the same parameter on all the loads. Then we have a certain operating cost that will be here. If we increase the uncertainty, we see that it increases, it can double here. So that is the price of uncertainty. It's like if you have to take a train or a plane and you know it might be late, or you have a connection and it might be late, then you will need to plan a very large time between the connections. So you will have an overall travel time that is larger than if there would be no uncertainty. So there is a cost on the travel time. Here there's a cost on the operation of the grid. Right? So that is the cost of uncertainty. There is always a cost of uncertainty. Of course, somebody can come a posteriori, an auditor can come and say, why did you choose some set point G2, G3 when we had told you that the prediction of the load was this and that, and you operated here, so you've doubled your cost. Why did you do that? A posteriori, we can say, yeah, you could have done that, but doing that a posteriori in a non-causal way is cheating. So there is always a cost of uncertainty, and this is affecting the grids. In the grids, we have so-called reserves. So what is typically done in the grids is that we need to put aside some capacity to allow for the uncertainty, and there is a cost to that, which is part of the cost of operating the grid. So the cost of operating a grid is not just to buy the energy for tomorrow at a certain price, but it is also to first buy it given the uncertainty. So we might be forced to buy a more expensive source of energy because this generator is the only one that's able to cover the whole range of uncertain operations, for example, and we will also need some reserves. And we see why, for example, we see that as the uncertainty increases, we are forced to put more and more power on G3 and less on G1. G1 is cheaper than G3, but if the load is very different from what is expected, the grid will not be able to sustain the power flow from G1. So we will have a blackout if the loads do an excursion within their uncertainty bounds. So it's not acceptable. We will see another way to solve, to mitigate the cost of uncertainty. The cost of uncertainty, as we've seen, increases. Here we have assumed there is no real-time control. We have to choose the set point for tomorrow, and once they are chosen, they will be fixed. So as a first approximation, this is what happens. But as we will see in reality, in grids, we will do also another kind of real-time control that we need to specify in advance, and that will ease a bit that problem. If we go back to the previous example also, we saw that when the uncertainty on L3 came to 100, the problem was infeasible. So in fact, if I would continue this curve here, we see that at 100 we have this cost, and then when we go beyond 100, the cost becomes infinite. It's impossible to run this grid. So here, in fact, we have at 100 is the maximum uncertainty we can sustain here. So infeasibility, we can view it as a special case of having very large cost. Here we have seen a simple form of stochastic optimization where I assumed that we can have the constraints satisfied with certainty here. Very often people do other modeling assumptions. They assume that the unknown loads satisfy some distribution that is typically derived from a Gaussian. Not always. Some people also use a beta distribution or Weibull, but let's do it with Gaussian here. So instead of saying the load will be, in the worst case, plus or minus 10%, I say, well, I don't know exactly, but it will be Gaussian with a mean, which is my forecast, and VI, which is the variance of my forecast error, my a priori variance. Now, what's the difference? If I do this, we very often use Gaussian distribution. By doing that, we very often ignore a fact of the Gaussian distribution, is that they are unbounded. If I say tomorrow the load will be 10 with a variance or a standard deviation of 1, that does not exclude the fact that the load will be plus 1 million or even minus 1 million, because Gaussian distribution has support on the whole set of real numbers. But this is a bit academic, because the probability that a Gaussian distribution is larger than 6 sigma, for example, is less than 10 to the minus 4 or 5. So the probabilities of seeing those values that are above a number of sigmas are astronomically small, but they are non-zero. So if we want to do it mathematically, we are forced to accept that some constraints are violated with some probability. That we will see in a minute here. So if we assume this, first we need to redo a bit of things on the cost function. Now, the cost function here is to make things even more difficult, and I assume the cost is quadratic in the generation. In the problems we saw before, there was nothing specific about the cost. The only difficulties were on removing the constraints, the disturbance from the constraint. Now let's focus on the cost. If the cost is quadratic, then we need to know something of the distribution, because now it's nonlinear. It's not only the mean that matters. So the cost of G2, G3 is the expectation of this. This one is G1, G2, and G3. G2 and G3 are not random. They are a control variable. But G1 is random. It depends on the random values L1, L2, L3. So this is the expectation value of, I think there is a C1 missing here, of C1 of this. And this is a random variable that is a linear function of G2 and G3. So its mean is minus G2 minus G3, sorry, a function of L1, L2, L3. So its mean is the linear function of the means. And the variance is the sum of the three variances, V1, V2, V3. So this is a Gaussian random variable with this mean and this variance. So the expectation of the square of a random variable is its mean to the square plus the variance. So this is the expected value of this. So that gives us the expected cost, which, as the program says, we should make a function of only the control G2 and G3, which is exactly what we have. Now we have a quadratic function here. And we see that the variance of the disturbances starts to play a role in the cost. Well, I will do a break, and we will see after the break how we get rid of the rest of the difficulties in this example. We are studying the case where the problem to solve is assuming the disturbance follows here a Gaussian distribution. We have seen that this affects the cost. Let's see how it affects the constraints. As we discussed a few minutes ago, we cannot now put deterministic bounds because the support of the distribution is infinite. But we can say that some inequalities have to be true with some probability. Then it's fairly straightforward, apart from a small subtlety here. We want to say, for example, that those three inequalities, we want to replace the generic problem by one where those three inequalities are true. So in other words, we want to say those three inequalities, we believe they are true most of the time. But exactly what it means is with probability small, for example, 1 minus epsilon. So here we take a very small epsilon, 10 to the minus 4. So with probability 99.9999, these three inequalities are true, right? Now, which values of the eta should we choose? Well, because we have three inequalities, those three inequalities are true means each of the three must be true here. In particular, if any of the three are violated, then the inequality are not violated. So we find that we have to set the value of the probability with which each of those inequalities is true to a value larger than the final value. They are mathematically related by this relationship here. If we want that with this epsilon, the three inequalities are true, then we must make sure that each individual inequality is true with a larger probability. The probability of failing it is even larger here. Approximately, if epsilon is very small, epsilon is equal to 3 alpha. The probability of violation of each must be 3 times smaller than the total probability of violation. So that's basic probability. Apart from this small subtlety, then there is no big difficulty. So what we have done in particular is once we have replaced those, the constraints by these here, we have, exactly like before, we have bounds on L1, except instead of having bounds that are given by a specified value a priori, we have computed them from the probability of violation that we have accepted. The only thing important to know about this is that it has a name. It's called chance constraints. So when I have a framework where the disturbance is following some distribution, we find a coverage area for the set of distribution that covers with probability 1 minus epsilon. Covers means with probability at least 1 minus epsilon, the constraints will be in this set. And a simple way to find such a set, if the three things are independent, is to find coverage intervals like I gave here. So in summary, if we are in the framework of stochastic optimization, we want to minimize the expected cost subject to the probability of the state being larger, feasible, larger than 1 minus threshold. And by writing this, I'm making explicit that what we'll need to do is to eliminate the state from those inequalities. If we have made everything linear, then we will have simply a standard robust optimization problem that can be transformed into a standard linear program or a standard convex program if the cost is not linear, like with the technique we've seen a minute ago. So in other words, stochastic optimization with chance constraints immediately will be translated into a stochastic optimization with certainty constraints and with the modification we've seen, a standard linear program. Before we move to the next case, I'd like to ask you the following question, which is often asked and puts the finger on one of the things we have to do when we model grids, or in general when we do stochastic optimization for processes. But again, that's the bread and butter in smart grid. We always have to if you read the transaction on smart grid papers, at least more than 50% of them are starting with an optimization problem. So the stochastic optimization problem. So this is really the bread and butter. Now the difficulty in stochastic optimization problem is the transformations of the problem. Because if the problem is not convex, probably for realistic cases, you will not be able to solve it, so you will have to make it a convex problem by some trick, which may be difficult for the AC equations. But once you have done that, the difficulty is, like in the lab, to transform the problem to make it fit into one of the boxes that we can solve. Here is an example. I'm showing you an original problem, which is this one. You will see it's a bit different from the one we had before, because there's no quantifier. And I'm asking you which of the two problems, if any, is equivalent to this one. The majority says B, which is the correct answer. The first problem is saying, well, we have an objective function that contains only the G variables, but there are other variables, the L, that are present in the constraints here. So that's a very frequent case. Very often we see optimization problems that are posed with a number of variables of interest that appear in the cost, for example, plus zillions of state variables or intermediate variables that appear in the constraints here. So that's a very standard problem. This one has a quantifier in the constraints. When you see quantifier, then you should stop a while. If there's a quantifier, think about it. So this problem is P is different from A, because A is a problem where the optimization variables are only the G, G2 and G3. This one is a problem with the optimization problems are G2, G3, L1, L2, L3. I did not write in subscript because that's what people very often don't do. So I wanted to force you to remove the ambiguity. But here the optimization variables are the three, the G and the L. Implicitly, the P's were constants here, where, of course, if we have to optimize on this. So those are the 5 optimization variables. Here, there's only 2. Why is there only 2? Because when you put a quantifier in front of a variable, it becomes a dummy variable. It's like the x in an integral of cosine x dx. The result does not depend on x. Depends only on the bounds. So similarly here, those constraints, you can test them for G1, G2, and G3, and they are, if I give you G2 and G3, you can test whether those constraints are true or not. And I expect an answer, yes or no, as a function of G2 and G3, not as a function of G2, G3, L1, L2, L3, because the question asked is, does there exist an L1 and L2, L3? Right. So that is a different problem, and this one also, but now the quantifier is for all. Certainly B is not the same as P, because P is saying I need to find G2, G3, and some L that satisfy the constraint, and to minimize this here. The question is whether A is the same as B. So exactly the same, certainly not, because they have different variables, the variable set, but they are equivalent in a sense that if I solve this, I will find a minimum cost, and I will find some values of G2, G3, and also L1, L2, L3 at the optimal value. And the G2, G3 that I will find here are the same as the G2, G3 I will find there. And the optimal value also, because the cost function is the same. And conversely also, if I solve this problem, I'll find some G2, G3. I know for this G2, G3, there exists some L1, L2, L3 that satisfy the constraint. So if I pick one triple of L values that satisfy the constraint, I add it to the variable, I will find a G2, G3, L1, L2, L3 that satisfies the constraint and has the same cost function. So more or less obviously, they are the same here. Those two problems are the same here. That is obvious to some of you, but not all, so it's important to realize it. If you are worried about why it's not the same in general, we can say that if I have a problem of the general type, minimize a function of x, so the function to be optimized depends only on x, but there are other variables, y, that appear in the constraints, then it's the same as minimize f of x, or it's equivalent to minimize f of x, subject to there exists y that satisfy the constraint. Of course, if we put for all, then that's radically different. And you have a formal proof if you're worried about my informal explanation a minute ago. So keep that in mind. We'll use that in the rest of the lecture, but also in the labs and in practical work you will need to do. We have seen two forms of stochastic optimization. I have to warn you that there are millions, not millions, but a large number of variants of stochastic optimization. So stochastic optimization is a generic concept where there are many, many subtle differences in how the problem is formulated. We have seen a formulation that uses the mean cost or the expected cost. Sometimes people use something similar to the expected cost, but not exactly the mean cost. And we have seen that it can be subject to the constraints being satisfied always or with some probability. Some people do a difference in the objective function itself. Instead of considering the minimum cost, they will consider the worst case cost. That's something that will be useful in the next lecture when we talk about demand response. We will find that it's a convenient way to model the thermal constraints on a building, for example. So if we do this, that means that instead of taking the expected value of the cost, which is a function of u and the state, which itself depends on the control and the disturbance, we consider the worst case here. I call it worst case optimization. Sometimes it is called robust optimization. Sometimes it is called non-probabilistic robust optimization. It's non-probabilistic because there is no distribution assumption on the disturbance. We assume only worst case bounds. In that sense, it's more convenient. We make fewer assumptions. We just make assumptions on the worst case here. That gives a problem of this kind. Minimize over the control u, the max over d of the cost of u, f of u, and d. That must be true also for all d in d. So the constraints are not modified, but the objective function is modified here. We have seen last week how to transform a problem that has a max in the objective function. Then we will apply this. Using this technique, then what we will see is that in fact we can replace it by a problem that is exactly of the same kind as we had before. So let me take this for the same problem. Now I want to minimize the cost, which is the cost that is written here, but instead of taking the average cost, I take the worst case. So now it's the max over L1, L2, L3, where L1, L2, L3 must satisfy this. And in addition, we have also the constraint on for all L1, L2, L3 in the feasibility conditions here. So we have a problem of the kind min max CUD, where where the max is overall D that satisfies the constraint, and the constraint also have this quantifier. The technique we have seen last week consists in saying if I have a max of things, it's equivalent to the problem I have by adding a variable which represents the max here. Note that this is not a minimization problem over U and D. It's a minimization problem over U alone, but where the objective function is itself the result of another auxiliary optimization problem. So what I do is remove this max, which we have with the technique we have seen last week. We call epsilon the max, and epsilon becomes a supplementary optimization variable. And we require that the epsilon is larger than C of U and D here. So we see that now we have an inequality constraint with epsilon that depends on U and D is our disturbance. Now, if the cost is linear in U and D, that will give simply more variables and more inequalities. We have the U, the control, but also the epsilon. And at least in the case where the cost is linear or can be made linear, this will be a problem that has exactly the same form as what we have seen last hour. So it can be solved with the same techniques here. So this is, in the case of the linear cost, this is a minimum addition here. So in this case, this will give this. So the epsilon is larger than this. This is the cost function here. And this epsilon must be larger than this for all L1, L2, L3. Then we need to compute the worst case of the left-hand side here. So we put that on the other part. We have to solve an optimization problem for this. And that will give, for example, for the specific values of the uncertainties, this will give this problem here. So, of course, the cost that we find here will depend on the uncertainty bounds for the disturbance. Voila. Other than that, this is business as usual. A third case, which is not business as usual, is when we introduce some feedback. In fact, when we have stochastic optimization, we will often find cases where the problem becomes infeasible if we have realistic disturbances. And this is because we are saying, I want to find a set point of my plant, of my grid, that will work for all values of the disturbances, of all the loads and the PV production, without assuming, and I have to decide today something that works for all cases. So very often that forces you to have largely over-dimensioned systems. If you can adapt to the change in the disturbances, then of course you can live with something more economical. For example, in a grid, if I have this grid here and I say if the loads are a bit more than what was forecast, there are controls, real-time controls that will occur. The first form of real-time control is called primary control, which I'm sure you've heard of. So what is primary control in electrical grid?
Stabilizing the frequency?
Stabilizing the frequency, exactly. So it's also called frequency control. So primary control is about detecting the power imbalance in the grid, so there is more production than consumption, or vice versa, and then changing the generator set points, or in the future also the consumer set points, to bring the balance back. So that is called primary control. It's called frequency control. Why is it called frequency control?
When the frequency decreases, we have not enough power in the grid, so we know because you can directly measure that, we can know that we have to increase the power.
So when the frequency decreases, we have power imbalance. We have not enough production. But why is that? Why is the frequency a symptom of the power imbalance?
Because the difference in energy gets stocked or taken in the rotational energy of the rotor of the generators. So if you have an imbalance, you either increase or decrease the rotational frequency.
Exactly, because we have rotating masses that are producing the electricity, that are generating electricity. And if you pull more than the rotating masses are expected to produce, what do? They slow down. It's like on your bicycle, when you start a slope, then it's more difficult and you slow down, right? So the slowing down reduces the frequency if we have synchronous generators. So this term frequency control comes from the legacy grids that are fed by synchronous generators, the turbines of the nuclear power plants, for example, or the big gas generators are of that type. In the future, if we have microgrid that is operated only by batteries, solar and solar panels, for example, that go through inverters, there is no rotating mass. Even if you have wind energy, the rotating mass are interfaced to the grid by DC-AC conversion. So there is no longer this dependency from the frequency to the power imbalance, which is one of the challenges in the smart grid, is to be able to detect the power imbalance without the symptom of frequency. In the extreme case, if you have a grid that has no rotating mass at all, the frequency will be constant. If your slack bus is given by a battery, the battery will give a frequency, and physically the frequency is completely synthetic. So what people have proposed to do is to emulate the inertia of rotating masses by measuring the power imbalance in the grid, and when the power imbalance becomes smaller, or when there is a power imbalance, vary the frequency, but that becomes artificial. The problem is that in grids of the future, or even now in some days, that we're approaching those days in the spring where there will be a lot of sunshine and a lot of wind, there might be a majority of generators that are non-rotating mass, non-synchronized rotating masses. So they will not respond in frequency. So even though we still have those big rotating masses, the frequency signal is becoming less significant. So that's one of the problems, and those problems are solved typically by having more advanced controllers. So what those controllers are doing, either directly in the case of frequency or indirectly, if we have more advanced controller, is that they are able to sense the power imbalance, for example, by having PMUs that measure the power flow everywhere. Then if you have a control that senses the power imbalance, it will instruct some of the generators to send more or less power. In traditional generators, this is the governor of the turbine that will implement what is called droop control, a linear feedback law that will accelerate or decelerate, or that will increase or reduce the power generation of a generator as a function of the power imbalance. So let's redo our exercise here, assuming we have G2 that follows this. In practice, the grid code today says if you have synchronous generators in a grid, you should do it everywhere. But here, let's assume only G2 does it. That means that the value of the power that is output by G2 is not a fixed constant that, like we had before, we said before, G2, we decide day ahead what it has to do, and we set it. Instead, what we decide is the parameters of the droop control. So the nominal set point, which I call U2, you have to generate this, plus you generate something that depends linearly on the power that is power imbalance, that is effectively measured at some point in time. Now, I said U2 is the power set point. It's not exactly. So L1, L2, L3 are disturbances that can vary around the central value, L1 bar, plus or minus 10%, for example. So V2 times the central value plus U2 is the nominal set point. I'm instructing generator 2 to do this. But I am assuming now that in reality it will adapt. So if the true value is not L1 bar but L1, it will do V2 L1 bar plus, which is part of the fixed set point, plus V2 L1 minus L1 bar, which is the zero mean disturbance, the shifted disturbance. And V2 is the slope of the droop at the generator here. So now my problem becomes, if I have a generator like this one, day ahead is to do two things. Set the midpoint of this, which is U2 plus V2 L1 bar plus L2 bar plus L3 bar, and also set the slope of the droop control here. So I have two parameters to set. And if I do that, I expect that my generator will, I will have more flexibility. I have the day ahead to decide on those parameters, but once they are decided, they will be able to better adapt because G2 will now provide some flexibility to the system here. From a control theory viewpoint, this is called a disturbance feedback. So the control depends on the fixed values and something that depends on the disturbance here. What we would like ideally is to do state feedback. We would like to have the state of the grid and then adapt to it, but mathematically it's very difficult to solve problems where we have state feedback. It's possible, but those techniques are a bit clumsy very often. Instead, what works very well, as we will see, is to take disturbance feedback. So this is a very generic form of control that is applied practically everywhere in all kinds of plants, and we will see how to solve them practically. We are still able to do some forecasts. So the nominal set point, as I said before, G2 bar is U2 plus V2 L1 bar, L2 bar, L3 bar. So the bar values of the L are supposed to be known in advance. That's my forecast, for example. My control decision now is U2 V2, from which I will deduce an average set point G2 bar. And the actual value is written in this form. So we can, an equivalent way to parameterize the problem, you find this way or that way, depending on the papers. In that way, we see, I could say, instead of saying that I have to decide on U2 and V2, I could say that I have to decide on G2 bar and V2, which are equivalent. There's a one-to-one mapping when we know the L bar between those two formulations. So let's do it now in detail. We have now to decide on the two parameters of my set generator G2. I assume G3 is like before, a static, not dynamic generator. The disturbance is the same as before, and the state is the same as before. I can compute the expected cost easily if I assume everything is linear. Then it will be given by the expected cost. So G3 is fixed. G2 bar is also fixed. So the 700 comes from the sum, from those sum of the L bars here. And the cost G1 depends also on my control. Now this is the G2. This is the G2 that we have here. Now what are the constraints? The constraint is that for all values of the load within my uncertainty bounds, that the generator set points are within their bounds and that the power flows on the lines are also within their admissible bounds. So the first lines of inequality is for generator 1, and the 3 lines of inequalities are for the 3 lines here. And we find, I put in red the control, in blue the disturbance, then we find that there's a difference with the problem we had before. In the problem we had before, we had red and blue, like here, but we had no mixed term that was both red and blue. Now we find some. So we have a problem that is not of the same type as the one we had 1 hour ago. It's a problem of the kind minimize the cost of the control. That's good. The control is only appearing the cost as expected. But where the constraints are for all values of the disturbance, we may have some constraints on the control also. But the constraints that mix the control and the disturbance have a term that is linear in the disturbance and linear in the control, but is not separated. So one way to write it is to say that for every constraint J, I have a matrix B such that I have a product on the left by D and on the right by U. That's a way of writing something that's linear both in D and U, so it's bilinear if you want. But it's not separated. Before we had a separated thing. So the problem is now how to solve a problem of this kind. It's also a robust optimization problem. And what we will see is what is the standard technique for solving this. So the problem is, of course, to get rid of D in this, so to make the constraints explicit in U only. And for this, we will use the dual linear program associated with each of the constraints. So I consider each of the constraints now. So this constraint has to be true for all D. So I look at the part of the constraint here where there is D. So there is also a part in U, but this will be constant with respect to D, so I can ignore it. So I consider an auxiliary problem that has to do with maximizing this quantity with respect to all possible value of D here. Right. Why maximizing? Because that's the trick we have seen many times, saying that this plus that is always less than this, and this has to be true for all value of D, then it means it has to be true for the worst case, because this is less than, and the worst case occurs when we have the max of this. Right? Another way is to put saying that this is less than that minus the right-hand side for all value of D is equivalent to saying that the max of all value of D is less than the right-hand side. That's a transformation we have used many times today and last week. Here. So the problem we have to solve is this one. Find the max of this subject to D here. If I call Pj star the max, it depends on U. Why does it depend on U? Because the coefficients of this program, that's a linear program in D. Now I have D transpose and D not transpose, but this here is a number, so it's the same as U transpose B transpose D, right? So it's everything linear in D, right? If the result of a matrix multiplication is a number, it is equal to its transpose. So you can write it, or its transpose, you have the same thing. So this is a linear program, right? But it depends, this coefficient of the linear program depend on U. So I call it Pj, there is one for each of the constraints, and it depends on U. So I call it Pj star of U. So if I can make sense of this, if I can compute Pj star of U in closed form, I would be able to remove the robustness, and I replace the jth inequality constraint by this, which is now a constraint on U only. Right. Ideally, that's what I would like to do. Now, we'll see we don't do this exactly, because finding Pj of U exactly might be a bit difficult to write it in closed form. Instead, what we will do is we will consider the dual of this linear program. So what is this linear program? This linear program that's the program that is written here. That's a linear optimization program with respect to the variable D with linear inequality constraints. So we have done last week this exercise of transforming a linear program into its dual. And I've just said that it's a completely automatic and stupid thing once you understand the notation. Once first you have the good reference, which is this one, and once you write it in the standard form, we find, so I'm redoing exactly what we did on the board last week. If I have a program of the kind maximize AD subject to DD less than C is the same as minimize C transpose lambda, such that lambda larger than 0, D transpose lambda equal A. So we see that the C which was in the constraint has become the coefficient, and the A that was in the coefficient has become the constraint. Now there are always subtle things like why do we have this lambda larger than 0? Why not? Well, those are the typically annoying things in optimization, and to avoid them, the method I propose, at least when I tested it, it always worked for me, is to always come back to a single problem, which is Boyd and Vandenberg's formulation. And then this formulation will give you all the necessary elements you have. So we have a completely mechanical way of transforming this into that I will now apply to my problem. So the dual of this problem that we had before can be cast into a minimization problem with inequality, with non-negative Lagrange multiplier and an equality constraint here that are exactly the one we obtained here. And we know by strong duality, because everything is linear here, that the optimal value of this one is the same as Pj star of u. Therefore, the condition, that's the theoretical solution we would have to remove the disturbance, Pj star of u less than gamma minus au, is equivalent to, because Pj star is a min, right? So saying that the min is less than something is equivalent to saying there is one value of the objective function that is less than this something here. Again, it's the same transformation we've done many times, but now if a mean is less than something, it means at least one of the values was less than this something. If a max is less than something, it means all the values are less. If the mean is less, it means there exists. So we see that max and min can always be used to remove there exists or for all. Now, which one we use depends on the case. So this problem is the same as this one. There exists a solution of a feasible point of this optimization problem such that the objective function is less than our right-hand side here. Therefore, now we have seen that having there exists quantifier in the constraints of a problem is equivalent to adding those variables to the big optimization problem and keeping the constraints. That's the quiz we did a few minutes ago. So this constraint, we can feed them back into the problem, and therefore our original problem is equivalent to the same cost function, but now we have added one Lagrange multiplier per inequality constraint, and we have changed the inequality constraints that had the disturbance by one that has the Lagrange multiplier. But now there is no quantifier at all, so we have a standard optimization problem. At a cost, we have added one Lagrange multiplier that has the same dimension as the C, the right-hand side of the constraints, per constraint here. So, in summary, whenever we have a problem of this kind, so that's a quite generic result, that any robust optimization problem where the disturbance and the control appear linearly but jointly can be replaced by a problem where I add one vector of Lagrange multiplier per constraint with same dimension as C, the C that is here, and where I replace the quantity here, everything that is in blue, is replaced by C transpose lambda j. So this value here that was depending on u now does not depend on u and does not depend on the disturbance. With additional constraints on the Lagrange multiplier that are derived from the different elements of the problem. And if there are other constraints on the controls that were independent of D, of course, they remain here. So we have gotten rid of this problem. At some expense, we have largely increased the dimension of the problem, but we have removed the original difficulty here. Well, that's the major step. This is how we solve those robust optimization problems that have this additional difficulty here. Well, that's a recap of what I just explained. Well, I did it for this example. I will not write all the details. I mean, this is just MATLAB programming, so you just need to write for each of those things, find the way how to write in MATLAB those constraints, which is now the most difficult part of this. But what I did is to solve it. So I solved it by increasing I solved it for various values of the uncertainty bounds. And we see that the cost is decreased. So the cost is the red line here. We find also what is the set point of the generation on G2 and G3. So the curve we had is a bit similar to what we had before. The blue curve is what we had if I do not have a fine disturbance, which can be cast in our framework by saying if I force the constraint that V2 is equal to 0. So there is no adaptation. So if the generator G2 is not dynamic, does not adapt, this is what we had before. And we had, when we reached 100, the problem was becoming infeasible. So we see here that we reduce the cost, not very much, but the main gain here is that we increase the domain of feasibility. There is a whole area here. We can almost double the uncertainty where the problem becomes feasible. So we reduce the cost and we make also the feasibility larger. Still, there's no magic. Even with some linear feedback, there is a point at which the thing breaks. If there is too much uncertainty, then the problem still becomes infeasible. Right? It becomes infeasible when we are close to 200 megawatt of uncertainty for this load, for example. We see also how the expected generation varies. We see it's non-linear. Not monotonic here, and also how the gain is set. We see that the gain V2 is 1 for this fraction here. That means we react very largely, and then we react less and less to the imbalance, because probably the generator set point G1 here becomes the limiting factor. I said we don't do it in detail, but if we do it, we are confronted with a number of technical problems. Like, for example, here, what is the dimension of the added complexity? What is, what is, for example, the number of constraints we have here? And the correct answer is, so the majority says D, which is 6. And the correct answer is not 6, but is 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 here. 1, 2, 3, 4, 5. 10 here. So those are all the things where we have blue and red, and there are 10 of them. What's the dimension of the matrix D? Well, the correct answer is the missing one. Is C. Well, that shows where the difficulty is in applying this. It's about screening exactly the things. The disturbance has dimension 3, so it has 3 columns, and there are 6 inequalities. Therefore, it has 6 lines. I will skip the next poll, but I will give just the answer, because we're running out of time. Then we will find that in total we have 10 constraints. The dimension of every lambda j is 6, the number of inequalities. Therefore, we're adding 60 variables to the original problem. So we had a problem with a control of dimension 3, and we add 60 variables. So there is a cost to that form of robust optimization. This cost is bearable if the problem is a linear program. This is why there's a lot of incentive in making everything linear. And if it becomes linear, then it is completely tractable. I will recap on saying what we have seen here. So we have seen a number of tricks, which are the standard ones used in the smart grid to solve the kind of problems we're confronted with, where we have both control and disturbance. And I've mentioned also the fact that whenever you can, it's always better to compute an optimal policy than an optimal set point, because an optimal policy will give you more flexibility. And we've illustrated here that our optimal affine feedback disturbance policy gives doubles the area of uncertainty. So the policy means the dependency from the state or from the disturbance and the control to the set point here. So from a state to an action, this is called a policy. What we have seen is linear things. We call them affine, there's plus a constant. There's a general theory of abstract policies, but when things are not linear, very often they are very difficult to handle. So those are the things that are most often used in the context of the smart grid. Voilà, that's all for today. We're done with the lecture. After this, we will do 1 hour for those who want to stay in the class. Where the TAs will be present in the class to help again with the lab. The lab will continue on Friday, and the first 15 or 20 minutes of the lab on the coming Friday we'll do a quiz on these questions. Thank you very much.